Okay, so let's demonstrate the one condition test in EMSE. We'll pick up where we left off in a previous recording. We used the event pipeline to make two averages, a face average in an N170 face perception task within a single participant, and a car average in the same participant. We noted that when the event pipeline made the averages, it also made metafiles for each average. So the face average has a metafile which points to all the single trials that go to make up that average. So for example, we're looking at the first single trial, here's the second single trial, and so forth. And the events, which were originally coded as from 1 to 40, the face stimuli, now they're all just called face, which is the name of the bin that we assigned for this average. Same thing with the car. So now the car average also has a metafile which points to all the single trials. Okay, in the last time we used these two metafiles to perform a permutation test of the differences between face and car. And this time let's look at the one condition test. Okay, so let's go to Statistics, one condition test. And let's see here. Let's let our interval of interest be negative 0.1 to, let's say, 0.4. And let's make a custom filtering interval. Let's pad it a little bit on either side. And let's increase our iterations this time. Let's do 500. Okay, so with 500 iterations, our P resolution can be as small as 0.002. A point here is that we don't have an option in the one condition test for multiple comparison correction. That's a point we can discuss further. There are some theoretical reasons for this, but I think it's worth giving some extra consideration as how we can correct for multiple comparisons. But in the meantime, we will get uncorrected p-values out of this test. So one point there is that there will be no benefit to restricting the interval of interest to a very small time interval. Okay, I'll say next. And let's do the faces first, so I'll select the metafile for faces. Next. Now we just have one condition called face. Again, the criteria will have been those that were used when we created the face average, because we're using the metafile that corresponds with that, so we don't need to select any additional criteria. So I'll say next. Let's do polynomial detrend that with a 0 order, that's baseline correction. We'll use the pre-stim interval of 100 milliseconds, and let's say finish. Alright, so as before with the permutation test, EMSE is preloading all of the epochs for faces. So they're preloaded. Now EMSE is generating what's called a plus-minus null distribution. This test is also called a plus-minus test. And the reason for that is the null distribution is generated as follows. For each of the 500 iterations that we selected, EMSE goes through each of the single trials and essentially flips a coin. If the coin comes up heads, EMSE leaves it alone. That's called the plus case. It's like multiplying it by +1. If the coin comes up tails, however, EMSE multiplies the whole everything by -1, which flips the polarity to be negative. Okay, so that's random. Each and every trial has an equal probability of coming up heads or tails, plus or minus. And so the expected value of the average will be a flat line. That is, expected value is 0. But, of course, it won't be exactly 0 in any of these cases. There will be some fluctuations around 0, and this is what we're calling the null distribution. So, that's what EMSE is doing now, generating the null distribution, against which the original average, which is essentially all heads, all unaltered, that original distribution will be stacked up against the rank ordered plus minus null distribution. Okay, so the result is there. Let me make a new folder and just call it, looks like I clicked 2 times there. Let's delete that and rename this new folder. Let's call it plus minus. Alright. Then that folder, the result file, will generate a few files, but all the files will begin with face. Whatever I enter here will be the prefix, if you will, of the files that get generated. So I'll say save. Let's make a new project, and let's call this project plus minus. Okay, so the files that were just generated, the data time series, are in this plus minus project. As we did before, let's add a probe to this project. That's out here in the resources. Let's add the biosemi probe. Okay, and now we've got some statistical results. So we've got the face mean. So if I look at this one, it should look similar to what we saw before, although my intervals are different. But essentially what we're looking at here is the average that we got up here for the faces with a different epoch. So that was regenerated in this test. Then we have a series of p-value files. So the first one is the p-value for the non-zero mean. Okay, so that means whether it's plus or positive or negative, these p-values will look for deviations from 0, whether they're positive or negative. Then we've got another one, which are deviations from 0, positive deviations, and a third one, which are deviations from 0 that are negative, that is less than 0. Okay, so since we're, for example, if we look at channel B10, here we have a latency at 187 milliseconds, where it's negative 15 microvolts. We might want to know, although it's pretty obvious from looking at this that should be significant, but let's see what came out of the test. Okay, so let's do this one. And let's go to channel array mode and let's look at B10. What we can see, so these are uncorrected p-values. So for that reason, it looks different than the corrected p-values we got in the permutation test. But what we see here is a very stable range of p-values around 200 that are very small. And so for example, let's see if we wanted to map that. Let's add a scalp, wireframe. Let's add a scalp. Okay, and load that. We could map in this range here. Let's say contour over map. Let's let our p-values be, say, 0.1. Apply. Okay, so these are p-values, and what we're seeing here are the small p-values are showing up blue, and there's some on the right and some on the left that are showing up very significant. Since these are uncorrected values, the flip side of this is the positive p-values that are close to 1. These are also significant in the other direction. However, with the caveat that it hasn't been corrected for multiple comparisons. Okay, let's do the same thing for cars. Okay, so let's save our workspace. Let's go to statistics, one condition test. This time let's do it the same way, but this time instead of selecting the face metafile, we'll select the car metafile. And let's select the car here, and everything else the same. Let's let this go. So this will take a bit. Let me just pause while this completes. Okay, we're nearing completion here. Okay, so this time let's go back to our plus minus folder. This time let's let car be our prefix for all the files that will get generated. And this time let's add it to the same project called plus minus. Okay. Okay, so here they are. So now we have a car mean. This one is a reconstruction of what we had up here, but with this time with a somewhat different interval. And now we might want to look in the same condition for negative deflection. So let me load this one. Let's go channel array. We might look at B10 again. Okay, so this is channel B10. We might notice that we have this same time interval similar to the one we had for the faces. Well, let's look at that one. Okay, let's do contour over the map. Let's let the contour lines be p-values of 0.1. Okay, somewhat similar, but looks like there's a bit of the occipital distribution definitely looks different here. Once again, there are uncorrected p-values, so the positive values here are could indicate significance in the other direction, that is for the positive going deflections. Okay, so that's a quick overview of the one condition test, which uses the plus-minus randomization procedure.